Imagine trying to fit the entire Library of Congress into a single standard-sized shoebox.
Right. I mean, you literally just can't do it.
You can't. You have to start ripping out pages or like shredding the covers, printing the text microscopically.
And eventually the structural integrity of the box just explodes.
Exactly. It just gives up.
Yeah.
Because you don't magically change the physics of the cardboard, right? You're forced to build an entirely different kind of container. And back in the 1960s, software engineers essentially tried to do exactly this with human language.
Yeah, they really did.
And the architectural fallout from that decision is something we are literally still dealing with today.
It's basically the ultimate story of architectural growing pains. You know, when you build a foundation for a small house and then suddenly decide that that house actually needs to be a 100-story skyscraper.
The workarounds get messy.
Incredibly complex, yeah.
So, welcome to today's deep dive. Our mission for you today is pretty simple. We are going to explore the hidden, often messy architectural choices that allow your computer to speak every language on Earth.
And it's quite the journey.
Oh, it is. We're going from the cramped 8-bit data limits of the 1960s to the vast, flexible systems running today's global software.
And if we connect this to the bigger picture, the stakes for you are remarkably high. Every single time you read an international news site or, text a friend in another language.
Or even just run a piece of code.
Right. You are relying entirely on the evolution of what we call the wide character, because without it, global digital communication literally breaks down into unreadable gibberish.
Which nobody wants. So let's set a baseline here. A wide character is, at its core, a computer character data type that has a size greater than the traditional 8-bit character.
It's physically larger in memory.
Exactly. It was engineered specifically to accommodate larger coded character sets. But to really grasp why that leap to wider characters was so revolutionary, we have to look at the tiny boxes computers originally forced language into.
We have to go back to the 1960s.
Yes. Okay, let's unpack this. Take us back.
So in the 60s, mainframe and mini computer manufacturers were all just trying to establish some common ground. Because before this point, different computers used completely different sizes for their basic data chunks.
Like it was the Wild West.
It really was. Some used 6-bit, some used 9. But the industry, heavily influenced by systems like the IBM System 360, began to standardize around the 8-bit byte.
And that became the standard smallest fundamental data type, the building block.
Exactly. That was the foundational block for storing information.
But they weren't using all 8 of those bits for the actual letters. Right. Like this goes back to the 7-bit ASCII standard.
Right, the 7-bit ASCII standard.
Which was the industry standard for encoding alphanumeric characters, mostly for those old teletype machines and early super clunky computer terminals.
Right. And 7 bits gave them exactly 128 possible combinations.
Which is not a lot.
It's really not. It was just enough to encode the uppercase and lowercase English alphabet, numbers 0 through 9, basic punctuation, and a few control characters.
Like what, carriage return?
Yeah, carriage return to tell the printer to physically go to the next line.
Okay, so 7 bits for the text, which leaves exactly 1 bit left over in our 8-bit box. That 8th bit.
The famous 8th bit.
Historically, this was used as a parity bit, which I like to think of it as the digital equivalent of packing peanuts.
Packing peanuts. Okay, I like that.
Yeah, because you're shipping a delicate package, which is your data, and you use that extra space in the box entirely for safety, just to make sure the package arrives intact.
That's a great way to look at it. To take that analogy a step further into the actual mechanism, here is how those packing peanuts actually worked. In the early days of computing, hardware was incredibly noisy and unreliable. Electromagnetic interference could literally flip a 0 to a 1 while data was moving through a wire.
Oh, wow. Just randomly in transit.
Just static on the line, yeah. So the parity bit was a clever math trick to catch that. If you had 7 bits of data, the computer would count how many ones were in that data.
Right.
If the number of ones was an even number, it would set the 8th bit to a 0. If it was odd, it set the 8th bit to a 1.
So it's forcing the math. The total number of ones in the entire 8-bit byte was always an even number.
Precisely. It always added up to even. So when the receiving computer got the data, it counted the ones. If it counted an odd number, it immediately knew, hey, a bit got flipped in transit. This data is corrupted.
Said it again.
Exactly. It was a brilliantly simple error detection mechanism.
But as computing technology improved, the hardware got much more reliable, right? The cables got better, the weird interference dropped.
Yeah, considerably, yeah.
And simultaneously, computers started to go global. Manufacturers looked at their 8-bit box and realized, well, the English alphabet isn't going to cut it in Europe or Asia.
No, they needed much more room.
So they dumped the packing peanuts.
They ditched the parity bit entirely, and by freeing up that 8th bit, they doubled the capacity of the byte from 128 combinations to 256.
Just by removing the safety material.
Exactly. This gave us the famous 8-bit extensions that became commonplace in the 70s and 80s, things like IBM code page 37 or PETC for Commodore machines.
Oh, PETC, yeah.
And the ISO 8089 standards. Suddenly, those early terminals had support for Greek, Cyrillic, Hebrew, and a bunch of other regional alphabets.
Okay, so you've doubled the capacity of your box, but here's the driving question for this whole deep dive. If we freed up the 8th bit and we got all these new alphabets, why wasn't that enough?
Well, because the math still maxes out at 256 combinations.
Right.
The fatal flaw of 8-bit extensions is that they were entirely region-specific. So you had one lookup table for Greek, a completely different lookup table for Cyrillic, and another one for Arabic.
But they all shared the exact same limited numeric space.
Exactly. The number 200 might mean a Greek omega on one computer, but on a Russian computer, that exact same number 200 meant a Cyrillic letter.
Which leads to what we call destructive translation, or what's affectionately known in the industry as mojibake.
Mojibake, yes. It's a great word for a terrible problem. Mojibake is that phenomenon where you open a text file or an email, and instead of readable text, it's a completely random string of wingdings, question marks, and accented gibberish.
Because the underlying binary data hasn't changed. Like the sending computer sent the number 200, but the receiving computer is using the wrong regional lookup table.
Right, it's blindly translating that number into whatever symbol happens to sit at slot 200 in its local directory.
And if you tried to actively convert data into a target set that didn't even have a slot for the character you were using,
the system would just replace it with a generic question mark.
and the original data was mathematically destroyed, you could never get it back.
It was a wildly unsustainable way to build a global communication network. I mean, you couldn't even have a single document with both Greek and Russian characters without writing incredibly complex, fragile, special conversion routines.
Just telling the computer to constantly swap its lookup tables mid-sentence.
Which is a nightmare. Which brings us to 1989. The International Organization for Standardization, or ISO, begins work on the Universal Character Set, or UCS.
The dream of one massive, multilingual character set to rule them all. No more swapping tables, right?
No more swapping. Every single character from every single language gets its own permanent, unique mathematical number.
But to achieve that, UCS required encoding values using either 16-bit, which is 2 bytes, or 32-bit, which is 4 bytes.
Right, and the 8-bit box finally shatters. It just physically cannot hold values that large.
So to store these new, massive character values in active memory, you needed a data type fundamentally larger than 8 bits.
And thus, the term wide character was born, specifically to differentiate these new, expansive data types from the traditional 8-bit ones.
Okay, so we made the data type bigger to fit the world's alphabets. We have a 16-bit or 32-bit wide character. Problem solved, right? Well, not exactly, because here's where it gets really interesting. Solving the storage problem accidentally highlighted a massive transmission problem.
Yeah, it really did. To understand this, we need to clarify a crucial architectural distinction. When we say wide character, we are strictly talking about the size of the data type in the computer's memory, the RAM.
Right.
A wide character does not state how each value in a character set is actually defined.
Right. The definition of the values is the job of the character sets themselves, like UCS or Unicode. The wide character is just the blank physical container sitting in memory, waiting to hold those massive definitions.
Exactly. So your wide character is sitting comfortably in your computer's active memory, taking up 16 or 32 bits of space, representing a complex kanji character or, a modern emoji.
Wait, I'm going to push back here.
Yeah.
Because if a 32-bit wide character solves all the space issues and prevents destructive translation, why didn't the entire computing industry just agree to upgrade the pipes?
What do you mean?
Like, why not just make the cables, the routers, and the internet protocols 32-bit across the board so we can just send these wide characters natively?
Because you are talking about replacing trillions of dollars of global infrastructure.
Yeah.
By the time wide characters were invented, the world had already spent decades laying undersea cables, launching satellites, and writing network protocols that were fundamentally physically hardwired to process data in 8-bit chunks.
You can't just flip a software switch to fix that.
No, you can't make an 8-bit physical router suddenly swallow a 32-bit object. If you try to shove a 32-bit chunk of data down a pipe strictly designed for 8-bit symbols, the hardware gets confused, it misreads the boundaries of the data, and the transmission completely fails.
So we have massive characters in memory, but tiny pipes for the internet. How do we get the data from point A to point B?
The engineering workaround for this transmission bottleneck is the multi-byte character encoding. And the most famous example of this today is UTF-8.
Ah, multi-byte. Because we lack those wide data paths, multi-byte encoding systems use multiple 8-bit bytes in a row to encode a value that is simply too large for a single 8-bit symbol.
Right. They break it down for transit.
And the mechanism behind it is brilliant.
Right.
Like in a multi-byte system like UTF-8, the very first bits of the byte act as a signal to the receiving computer, right?
Yes.
If the byte starts with a 0, the computer knows, okay, this is a standard, old-school 8-bit character. I can read it immediately.
But if the byte starts with a specific sequence, like 110, the computer knows, wait, this is incomplete. This is part of a larger character.
I need to grab the next byte.
Exactly. I need to grab the next byte and read them together to figure out the math.
You know, the C programming standard actually officially splits these two concepts up, which I find incredibly helpful for visualizing this.
Oh, the distinction between multi-byte and Y.
Yeah. According to the C standard, multi-byte encodings, those variable length chains of 8-bit chunks, are primarily used in source code, external files, and network transmission.
Right.
Whereas wide characters, the fixed, massive 16 or 32-bit containers, are the runtime representations of characters sitting in single objects.
They exist solely in the active, volatile memory of the system.
Right. It's basically like buying IKEA furniture.
IKEA.
Yeah, hear me out. Multi-byte is the flat pack you shove into your car for transit.
Okay.
And the wide character is the fully assembled bookshelf sitting in your living room's active memory.
Okay, that analogy actually holds up perfectly.
Yeah.
The assembly process is the runtime conversion your processor performs.
Exactly.
But here is where the history of tech giants makes things really complicated. Because different operating systems decided to build their living rooms and assemble those bookshelves at very different times in computing history.
Right.
And it created completely different architectural philosophies that still clash today.
The Great Schism.
The Great Schism indeed. Let's look at the early adopters. Systems like Microsoft Windows, the .NET framework, and the Java programming language.
The heavy hitters.
Right. In the early 1990s, they were eager to solve the internationalization problem. They wanted to be global immediately. So they jumped on the very early version of the universal character set, specifically a standard called UCS2, which essentially became Unicode 1.0.
And UCS2 was a strict 16-bit system.
Right. It offered 65,536 possible characters. And at the time, engineers genuinely believed that was more than enough space to encode every single living human language with room to spare.
Oh, the hubris.
I know. So Windows and Java locked their foundational architecture into a 16-bit wide character. In their systems, the default wide character, type like raw chart in C++ on Windows, or char in Java, was hard-coded to be exactly 16-bit.
Which seemed like plenty of space. But then we get the historical plot twist. Unicode didn't just stay with living languages.
No, it grew immensely.
Right, we get the 1996 update, Unicode 2.0,
Yeah.
and suddenly they are adding dead historic scripts, complex mathematical symbols, and eventually the thousands of emojis we use today.
The full range of human expression blew way past the 65,000 character limit. It expanded to require 21 bits of space.
So what happens to Windows and Java? They are already locked into an architecture that physically only has 16 bits of space per character.
They get stuck in what we can call the 16-bit trap, because they can't easily tear out the foundational architecture of their entire operating system without breaking millions of legacy programs.
It would be catastrophic.
It would. So these systems now have to rely on a complex workaround called surrogate pairs.
Okay, break down how a surrogate pair actually functions under the hood, because it sounds messy.
Oh, it is. Remember how we had 65,000 possible combinations in the 16-bit space?
Yeah.
Engineers went in and permanently reserved a specific block of those numbers. They explicitly said these numbers no longer represent actual printable characters. Instead, they act as warning flags. When the Windows operating system reads a 16-bit wide character and sees that it falls into this reserved high surrogate block, the hardware knows it cannot print a letter yet.
It has to wait.
Yes. It must hold that data in suspension, grab the next 16-bit wide character, combine the mathematical values of both, and then look up the resulting massive character.
So they are essentially duct taping two 16-bit boxes together just to store one single modern Unicode character, like a smiling emoji.
Basically, yeah. It's a massive workaround.
It gets very messy because it breaks a fundamental programming assumption. Their wide character data types no longer map one-to-one with actual printed characters.
No, not at all. One printed letter might be one wide character in memory, or it might be two.
Which forces programmers to write highly defensive, complex code just to count how many letters are in a word.
Exactly. Meanwhile, you have the Unix-like systems Linux, Mac OS, sitting across the aisle. What was their strategy?
Well, they took a wait-and-see approach.
They did. Unix-like systems generally waited until the dust settled on the Unicode expansion. When they finally standardized, they adopted a massive 32-bit write chart as prescribed by the C90 standard.
Why?
By going straight to 32 bits, they gave themselves enough room to comfortably fit the entire modern 21-bit Unicode code point into a single, solitary wide character container.
So no surrogate pairs required. Every wide character is exactly one printed symbol.
Precisely.
So if we look at the modern landscape today, for you, the listener, navigating these systems, you're dealing with two very different preferences born entirely from this history. Operating systems heavily influenced by Unicode 1.0, like Windows, tend to prefer using wide strings made up of these 16-bit character units.
Yes, whereas Unix-like systems, despite having that massive 32-bit wide character available to them, actually tend to retain the old 8-bit narrow string convention for handling text.
Wait, really? Even in memory?
Yeah. Because UTF-8 multi-byte encoding became so efficient and universally adopted on the internet, Unix systems prefer to just keep the text in that variable multi-byte format, even in memory.
Going back to the analogy, they prefer to keep the furniture flat-packed for as long as possible, only assembling it into a 32-bit wide character at the exact millisecond they need to manipulate it.
That's a great way to put it. The historical circumstances of when an operating system was built absolutely dictate what types of encoding they prefer to process today.
Which raises a really important question. How do modern programmers actually deal with this historical baggage? If the size of a wide character changes from 16 bits on Windows to 32 bits on Mac, how do you write a piece of software that works everywhere?
This is where we look at the language lottery, how different programming languages have actively tried to clean up this mess over the decades. And it really starts with the absolute Wild West of C and C++ prep.
Oh, man. Listen to how the original C90 standard defined the wide character data type. Raw chart, I have it right here.
Go for it.
It called it an integral type whose range of values can represent distinct codes for all members of the largest extended character set specified among the supported locales.
Yeah. That is essentially a legal loophole masquerading as computer science.
It really is.
They basically defined it as make it as big as it needs to be for whatever system you happen to be running on. It was entirely implementation defined.
Which creates a total nightmare for portability. If you write a program on a Mac expecting your wide character to hold 32 bits of data, and someone compiles that exact same code on an old Windows machine, where the compiler defines it as 16 bits,
your program crashes.
Right. It literally attempts to stuff 32 bits of math into a 16-bit physical box, causing memory overflows.
The ambiguity was so dangerous that the ISO-IE Unicode standard itself had to issue a staggering warning.
What did it say?
It explicitly stated, the width of raw chart is compiler-specific and can be as small as 8 bits. Programs that need to be portable across any C or C++ compiler should not use raw chart for storing Unicode text.
Wow. The global standard itself is telling programmers, do not use the wide character type to store global text if you want your code to survive.
Yeah, it was a massive red flag. So how did C and C++ finally fix it?
Well, it took until their 2011 revisions. Both C and C++ finally introduced fixed-size character types to the language. They explicitly created char16 for guaranteed 16-bit storage and char32 for guaranteed 32-bit storage.
Which finally provided unambiguous representations. They left the old write chart in the language as a legacy artifact so old programs wouldn't break, but they gave modern programmers new, precise physical dimensions to work with.
Okay, so that's C and C++ trying to patch the leaks. Let's look at Python's evolution, because I think it perfectly illustrates a massive realization in the tech industry regarding the wide character.
Python's journey is fascinating here.
It is. If you go back to Python 2.7, the language relied heavily on whatever the operating system dictated. Its character type was tied to the underlying C compiler's raw chart.
Still shackled to that unpredictable underlying system.
Right, but then by Python 3.3, they realized this was inefficient. They introduced a flexibly sized storage system for strings. The language would, dynamically look at a string of text, figure out the largest character in it, and then allocate memory based on that.
Smart.
But here's the real aha moment. As of Python 3.92, they dropped the use of chart for Python strings entirely.
It's a complete paradigm shift.
It really is. They realized that forcing text into these massive 32-bit wide character arrays in memory is actually a massive waste of RAM.
Oh, totally. Most text on the internet is still in the standard ASCII range English letters, basic numbers, which only requires 1 byte of storage.
Right. So if you force an entire English paragraph into a 32-bit wide character array, you are inflating your memory usage by 400% with empty zero-filled bits.
Just waste space.
Exactly. So Python decided to lean entirely into multi-byte flexibility. Now, they just store the text as UTF-8 multi-byte strings and cache it. Modern CPUs are so incredibly fast at decoding UTF-8 on the fly that keeping a massive wide character in memory is just obsolete.
They move from store it wide so we can access it fast to store it narrow because our processors are finally fast enough to decode it instantly.
Yeah.
And to add to that, on the complete opposite end of the spectrum, you have modern language like Rust.
Ooh. Rust took an intentional, uncompromising rebellion against the decades of pain caused by C+ ambiguity.
Absolutely. In Rust, a char data type is exactly 32 bits, and it represents a valid Unicode scalar value. Period.
No guessing, no compiler-specific baggage, no surrogate pairs.
None. The designers of Rust looked at the historical mess of 16-bit traps, variable-size chart types, and the constant fear of memory overflows, and they established an absolute physical dimension, 32 bits.
It solves the portability issue immediately by refusing to compromise.
Right. It's like they just built a living room so massive that you never have to flat pack the furniture ever again.
Which is wildly inefficient for memory space, but it is incredibly safe for the programmer.
Which showcases the eternal trade-off in computer science. You can optimize for memory space like Python, or you can optimize for unshakable stability like Rust.
So what does this all mean? When we step back and look at the whole picture, a wide character isn't just a dry technical specification.
No, it's really not.
It is a living artifact. It is the fossil record of computers painfully learning to accommodate the sheer, messy volume of human language. We started in these cramped 8-bit cardboard boxes, tried to squeeze extra alphabets into the packing peanuts, broke the box entirely with destructive translation.
Mojibake everywhere.
Exactly. And eventually, we had to engineer these complex 32-bit global memory systems just to say hello in every language.
The real takeaway for you listening to this is to appreciate the staggering, invisible labor your devices perform every single day.
It's mind-blowing.
It is. Whenever you type a character that isn't standard English, there is a massive mathematical translation effort happening under the hood. Your system is constantly switching between massive memory representations and narrow multi-byte transmission streams.
Juggling surrogate pairs and historical architectures.
Counting ones and zeros just to render that single text message accurately on your screen.
It is a minor miracle of engineering every single time you send an emoji. Which leaves me with one final thought to ponder today. If the entire history of the wide character is essentially a story of brilliant engineers chronically underestimating exactly how much digital space human expression requires, what future forms of human communication are we currently underestimating the storage for right now?
That is a profound question. I mean, spatial computing, neural interfaces, the data requirements will be unimaginable.
We'll leave you to think on that. We've gone from the 8-bit box to a 32-bit world. But human expression never really stops expanding, does it? Keep diving deep.